In this part of the data structure course related to trees, we will examine some example codes based on tree traversal, such as counting number of leaves in a tree or computing the depth of a tree. In this example, we will use post-order traversal to count leaves in a tree. The function is written as a recursive function, and it is written also as a template function. Template class is T. Here, as parameter, we are sending the pointer T, which points to the root of the tree, and an integer reference count. There is no return value from the count leaf R function, but here there is a parameter count, which is a reference to an integer. So the number of leaves will be stored in this variable. If T is not null, then this part is to be executed. Otherwise, it will return directly. We are using post-order traversal, so the function countLeafR is called with left link of the node pointed by T. So we are visiting the left subtree together with count. So it will be called for the left subtree. And recursively in the left subtree, further subtrees will be visited. And in the left subtree, further left subtrees will be traversed. When the left subtree is traversed, then there is a call to the function itself with the right field of the node pointed by T together with count. So this is to traverse the right subtree. After left and right subtrees are traversed, the node is visited. If T left is null and T right is null, that means that this is a leaf node, then the count is incremented. Here notice that left and right methods are applied on the node pointed by T, which return the related link fields of the node. That's the end of the function. The number of leaf nodes is to be stored in a variable count, and this is a variable to be defined before calling the function because this is a reference. And its value should be initialized to 0. Here there is another function whose name is countLeaf. This function is called by the pointer pointing to the root of the tree. In this function, we are declaring a variable countMyTree, which is initialized to 0, and then we are calling this function countLeafR with myTree. This is the root of the tree, and countMyTree, which is initialized to 0. So whatever the number of leaf nodes will be stored in count, which is corresponding to countMyTree in the function countLeaf. And then this function will return countMyTree. So if we call the countLeaf with the root, it will define countMyTree and it will call countLeafR with the countMyTree, but the value is initialized to 0 before calling the recursive function given here. Now on this example subtree, we are going to execute the code to see what happens while the code is executed. There is a call to the countLeaf with the pointer T given here. It points to the root of the tree. So here this pointer points to the root. Inside the function countLeaf, countMyTree is set to 0, and then countLeafR is called using arguments myTree and countMyTree this is pointing to the root of the tree, and this is 0. So here t is the pointer pointing to the root, and count is 0. On the figure, it is shown what is the value of count when the function count_leaf_r is called, and here also the value of the count when it returns from this node is also given here. So we are going to that node with count is 0, and then we have to go to left subtree. Still the value of the count is 0. From that one we go to left subtree, value of the count is 0. For this node, when the left subtree is to be visited, the value of the pointer is null, so it returns immediately. Then we have count_leaf_r, which is null again, it will return immediately. And then comes visit node. This is checking if left link and right link are null. So it is the case. So the value of the count is incremented. Count becomes 1. It was 0 when we visit this node, and it becomes 1. Then we go to the parent node, and the right subtree should be traversed. When it is to be traversed, the value of the count is 1. However, here we have a leaf node. The value of the count will be incremented. Here, when this subtree is visited, the value of the count is 1, and in return it will become 2 because this is a leaf node. Then the value of the count is 2 when we return back to the parent node. For this node, because this is not a leaf node, the value of the count is not changed, so it is going back to the parent node with value 2 of the count. Then we go to the right subtree while the count is equal to 2, and we go to the left subtree, count is still 2, visit the left subtree, count is 2. Because this is a leaf node, the value of the count is incremented in this line, and return back to the parent node having value of the count as 3. And here for this node, left subtree is traversed. There is no right subtree, so visit the node which is not a leaf node, then the value of the count is still 3. Then go to parent node and go to right subtree with count value as 3. Because this is a leaf node, the value of the count is incremented, it becomes 4. Then parent is visited. This is not a leaf node, the value of the count is same. Visit that node, and the value of the count is again 4. It is not updated because this is not a leaf node, and the function returns as the value of the count is 4. Here, this is a reference to this variable, and the value of the count my3 is 4 now. And then the function is returning the value of the count my3, which is 4. If we count the leaf nodes here, we have 1, 2, 3, and 4 leaf nodes. In this example, we will consider the function depth, which will compute the depth of a tree. This is implemented as a template function, and here notice that there is a return value from the function. This is different than the previous implementation. Instead of storing the value in a reference variable given here, instead of that, we are sending only the pointer to the tree as a parameter, and we are sending the value of the depth in the return value. Inside the function, the integers depth left, depth right, and depth val are declared. If the pointer t is null, then we are setting depth val to -1. If the tree is empty, depth is -1. If t is not null, we are going to execute the else part. The value of depth left is set to return value from the function depth. Depth is called recursively for the left subtree. When the left subtree traversed, then depth is again called for the right subtree. The return value is assigned to depth right. Notice that depth val is used to show the depth of that node. Depth val is set as 1 plus this value. Here we have an expression such that we have a condition here asking for if depth left is greater than depth right. So we have a condition. If this condition is true, then the first part is to be executed. If it is false, then the second part is to be executed. So it will check if left one is greater than the right one. Whichever is greater will be chosen as the return value from this part of the expression. And then 1 is to be added to maximum value selected here. After that subtree is visited, it will return back to the parent node with the calculated depth val. Now let's execute the code on a sample tree. The function depth is called with the pointer t, which points to the root of the example tree. The value of the pointer is not null, so we go to the else part. In the else part, depth left is set to return value of the function depth. There is a recursive call with the left subtree. So we go to left subtree, and here again we go to left subtree. For this node, if we go to the left subtree, t is null. So there will be a return value -1 from the function. Now the left subtree is traversed. There is a call to the function depth recursively for the right subtree. And for that one also -1 is returned because the link value is null. So for this node, depth left is -1, depth right is -1. This is not true, so depth right is chosen. So the value here is -1. -1 plus 1 equal to 0. So the value of depth val becomes 0, and 0 is returned from the depth function. So 0 is returned, and we go to the parent node. For this one, we go to right subtree, and here again -1 and -1 are returned from the depth function because they are equal. -1 is chosen and 1 is added. So 0 is returned from this node to the parent node. For this parent, 0 and 0 are compared, and 0 is chosen as the result of this expression, and 1 is added. So 1 will return from this node to the parent node. The left subtree is traversed, and now the right subtree is to be traversed. We go to right subtree, from there we go to left subtree, and from there we go to left subtree. From here we have -1, -1, and for that node, when it is visited, the value of the depth val is set to 0 and it is returned. So 0 is returned from the left subtree for this node. And also -1 is returned for the right subtree. 0 is greater than -1, so 0 is added 1, and 1 is returned from that node to the parent node. And also right subtree is visited, And from there, -1, added 1, 0 returns from the right subtree. Compare 1 and 0, this is greater, it is chosen, and 1 is added, 2 returns from this node to the parent node. Compare these two, 2 is greater, so it is chosen, 1 is added, and 3 returns from the function depth. So when this function depth is called by the pointer to the root of this subtree, 3 will return from the function. And if we consider the depth of this tree, this is level 0, level 1, level 2, and level 3. The depth is 3, so the depth is 3, and the value returned is also the same. It is 3. In this example, we will consider the function minkey, which will find the minimum key value stored in a binary tree pointed by t. We assume that tree is not empty. The function is going to be implemented as a template function. We have input to the function t, which is the pointer to the root of the tree for which the minimum key value is to be determined. And that value will be returned from the function as an integer. In the function, meanwhile, min_left and min_right are declared as integer. First, we check if the node pointed by t is a leaf node. For this purpose, we are checking if the left link is null and right link is null. If this is the case, it is a leaf node and return the data of the node. Otherwise, it is not a leaf node, and we are checking if left link is not null. If this is the case, then we are setting the value of the variable min_left with the return value from the function minkey, which is called for the left field of the node. As min_left is set to max integer, whatever the possible maximum value for the integer, that means that in that case, because setting the value to max integer, what comes from the other subtree will be chosen when compared, whichever is smaller. Then we are checking if the right link is not equal to null. If it is the case, minkey is called by the right link of the node pointed by t, and return value is assigned to the variable min_right. If it is null, in that case, similar to the left one, min_right is set to max integer. In this expression, we are comparing min_left, which is the minimum value stored in the left subtree, with min_right, which is the minimum value stored in the right subtree. We are comparing them, and then the smaller one is chosen here. If min_left is smaller, it is chosen. Otherwise, the value of the min_right is chosen, and it is assigned to min_var. Then we are comparing the data with the values stored in the node, and whichever is smaller is chosen as the value of this expression and stored into min_var. So by using this two lines, whichever the minimum, min_left, min_right, or the data stored in the node is chosen, and it becomes the value of the min_var, and min_var is returned from the function minkey. Now let's consider the execution of the code on an example tree. Here the function minkey is called with the pointer t, which points to our tree. For the root, it is not a leaf node. We go to left subtree and again left subtree. This is a leaf node, so left is null, right is null for the node, and the data is returned from the function minkey. So the return value is the data stored in the node, which is 19. Then we go to right subtree for this node. Because this is a leaf node, 31 is returned from the node having value 31. And for this node, 19 and 31 are compared in this line, and smaller one is chosen, which is 19, which is also compared with the data stored in the node. Because this is smaller, as the return value, 8 is chosen. 8 comes from the left subtree to the node here, which is the root node. And the right subtree should also be traversed. We go to right subtree. For that one, we go to left subtree, and we go to left subtree. For this node, the return value is 3 because this is a leaf node. Then we come to that node. For this one, from the left one, the value returned is 3, and also we have to check the right subtree, but for this node, the right link is null, so max integer value is set as the return value from this right subtree. These two are compared. 3 is smaller than max int, so 3 is chosen as the value when these two are compared in this line. Then the value is compared with 20. Because 3 is smaller than 20, 3 is chosen as the return value from this subtree. Then we go to the right subtree. This is a leaf node, and 15 is returned from that node. And here we compare 3 and 15. 3 is smaller. Then it is compared with the data stored in the node. Still 3 is smaller, so return value from this right subtree is 3. 8 and 3 are compared. 3 is smaller. It is compared to data in the node. Still 3 is smaller, so 3 returned from the function as the minimum key value stored in the tree. Here there is another function to find the level of a leaf node at minimum level. We are not going to cover this code in the video lecture, but it is available in the lecture notes, and you can trace this code on a sample tree to understand how it operates.